Welcome to 7.6, Moments, Centers of Mass, and Centroids. Okay, a mass. Mass is a measure of a body's resistance to changes in motion and is independent of the particular gravitational system in which the body is located. So your mass on Earth is the same as the mass on the Moon. Your weight's going to be different, but the mass will be the same. Mass on Jupiter would be the same. Weight would be a lot different on Jupiter. Not that there's a solid part of it, but anyway, there's gravitation would crush us on Jupiter. Okay, some people inaccurately equate mass to weight, and I remember when I was in high school, my biology teacher spent a great deal of time trying to distinguish between that before us students. So weight would vary. Weight is dependent upon the gravitational system. Mass is constant. You could be in space and have no gravitational force acting on you, and you still have the same mass. Excuse me. Force is mass times acceleration. Systems of measurement. So in the U.S. we have measure mass of the slug, and the measure of force is a pound. So get that. Pounds, when you weigh pounds, again, that's weight, that's not mass. We don't really use the slug. I mean, people use it, but that's not something that we learn how to work with. The international system, the kilogram and the Newton and the CGS, centimeter, gram, second, is going to be the gram and the dyne. Okay, but I think this international one's the most commonly used one. Okay, conversions. 1 pound is 4.448 newtons. 1 slug is 14.59 kilograms. 1 newton is 0.2248 pounds. 1 dyne is 0.00002248 pounds. 1 dyne is also 0.00001 newtons. 1 kilogram is 0.06852 slugs. 1 gram is 0.00006852 slugs. Almost seems like that one's backwards. And 1 foot is 0.3048 meters. No, this is right. That's right. Yeah, because it's 1,000 times there. Okay, let's talk about moments. And no, I'm not referencing the Whitney Houston song. No one's going to get that one. But moment about a point. The tendency an object has to move about a point. It's not actually moving, it's a tendency to move or rotate about a point. Moment of m about the point P. Moment is m times x. And x is the length of the moment arm. So the seesaw example. Here it's pretty balanced. Over here, there's more distance. So you'd expect this side to come down. And in this case, there's more distance over here on the left side. So you'd expect, even if they're same masses, this side to fall down. There's more of a tendency for this side to move down. This side would move up. Moment about the origin. The measure of the tendency of a system to rotate about the origin. Equilibrium is when all the moments sum to 0. So center of mass, the point x bar at which the fulcrum could be relocated to attain equilibrium. If the system were translated x bar units, each coordinate xi would become xi minus x bar. So x bar is going to be the sum, as I goes from 1 to n, of mi xi. So each mass times its respective distance from the origin, divided by sum I goes from 1 to n of mi, or the sum of all the masses. So it's the moment of system about the origin divided by the total mass of the system. So if m1 x1 plus m2 x2 plus mn xn equals 0, the system is in equilibrium. Moments of center of mass in a one-dimensional system, so just the x coordinate. Let point masses m1, m2 through mn be located at x1, x2 through xn respectively. The moment about the origin is MO, moment about the origin, is just the sum. The center of mass is going to be x bar equals MO over M. So basically we're dividing out all the M's, or this is the sum of all the masses. Essentially dividing that out. I mean, right now it's kind of a weighted amount. Weighted, that's kind of a play on words. But the point is, you divide that out and you get a location. Where would this be balanced? Where can we balance that? So in example 1, we're going to find the center of mass of the point masses lying on the x-axis. Okay. Let me draw a little picture here, a little diagram. Okay. At the -3 mark, we have a mass of 7. At the -2 mark, we have a mass of 4. At the 5 mark, we have a mass of 3. And at the 6 mark, we have a mass of 8. So x bar is going to be 7 times -3 plus 4 times -2 plus 3 times 5 plus 8 times 6 divided by 7 plus 4 plus 3 plus 8. That's the sum of the masses. This will give us 34 over 22, which is 17 over 11, and that would be approximately 1.55. So right about here is your center of mass. That's where it balances. Now, what's interesting about this, before we erase and go on to something else, I just want to look at this. 7 plus 4 is 11. So you have 11 pounds on this side of the origin. 3 plus 8 is 11. You have 11 pounds on this side. But because these masses are further away, it's got this moment that this wants to tend to go down over here. So if you put the balance mark here, you're in equilibrium and it's not going to tilt. Same masses, but this is further away, and that's why you have that tendency. And I know that's probably a, like a, oh yeah, of course, Jeff, kind of comment or concept. But I believe it was Archimedes that said, give me a lever, meaning a big stick, big enough and I can move the world. If you get enough leverage on something, it doesn't take a lot of force to move it. So if you had very little distance, you're trying to pick up 100 pounds, it's going to be hard. But you bring a long pole, you can prop that up if you have the fulcrum over here. Kind of like how we do with a jack on a car. Okay, I'm going to erase this now. I'm going to go on to the next one, so feel free to pause in the next few moments. Okay. Center of gravity is another clever name for center of mass. Torque, or moment about the origin. Torque is going to be equal to the mass times the acceleration. Center of gravity be the torque over the force, which is m naught a over mass times acceleration. Or sorry, that's the moment times acceleration over mass times acceleration, or just the moment over the sum of the masses, which is your center of mass. Okay. Center of mass in a two-dimensional system. So we do the one-dimensional system, we just have the x. Now, it becomes a little different if you do the moment and center of mass in the two-dimensional system. And this is a little more useful for us. Let the point masses m1, m2 through mn be located at x1, y1, x2, y2 through xn, yn. The moment about the y-axis is, now get this, don't stress about this now, my is m1, x1, not a typo, plus m2, x2 through mn, xn. And the moment about the x-axis is m1, y1 plus m2, x2 through mn, yn. So the moment at about the x, I do that one. The center of mass, x bar, y bar, or center of gravity, is x bar is my over m, y bar is mx over m. So those are the definitions here. Or of course the mass is m1 plus m2 through mn. Okay, example 2. We have a two-dimensional system. The masses and their locations, we have, let me draw this and graph this up here. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So we have mass at these different locations. At 1, -1, we have 5 units of mass. At 5, 5, we have 1. And at -4, 0, we have 3. So x bar is going to be 5 times 1 plus one times 5 plus 3 times -4. All over 5 plus 1 plus 3, and this gives us -2/9. Y bar is going to be, again, 5 times 1 plus -1 times 5 plus 0 times 3. Over 5 plus 1 plus 3, that will be 0 over 9, which is 0. So that means the center of mass, if you were to balance these, center of mass is going to be -2/9, comma 0. That'd be right about here. Okay. Planar lamina is a flat plate of material of constant density. That's important to assume that much, because if it's variable density, we're going to need more tools. It'll be more of a three-dimensional system. Density is a measure of the mass per unit of volume. Moments and center of mass of a planar lamina, like a plate. Doesn't have to be a round plate, it could be a rectangular plate. Let f and g be continuous functions such that f of x is greater than g of x on the interval from a to b. And consider the planar lamina of uniform density rho bounded by the graphs of y equals f of x, y equals g of x, and x between a and b. The moments about the x and y axes are mx, moment about the x-axis, is rho times the integral from a to b of f of x plus g of x over 2 times f of x minus g of x dx. The moment about the y-axis is rho times the integral from a to b of x times f of x minus g of x dx. The center of masses, x bar will be my over m, y bar is mx over m, where of course m is rho times the integral from a to b of f of x minus g of x dx. That's the center of mass of the lamina. So let's do some problems with this. Okay, find my, mx, and x bar, xy, x bar, y bar for the laminas of uniform density rho bounded by the graphs of the equations. Y equals 1/2 x squared, y equals 0, and x equals 2. So if you want to get a picture of that, a visual of that, so on this, here's 2 squared, it's 4/2 of that, this is also 2 there. Okay, so for the mass, m, little m, is going to be rho. And I'll be honest, most of the time, rho is going to cancel out. Integral from 0 to 2 of 1/2 x squared minus 0 dx, which is rho, times 1/2 of x cubed over 3 from 0 to 2. That's going to be rho times 2 cubed is 8 over 6. And that's going to be 4 times rho over 3. For mx, we have rho times the integral from 0 to 2 of 1/2, because remember it's f of x plus g of x over 2. We can say 1/2 of 1/2 x squared plus 0 times 1/2 x squared minus 0. So our f of x is 1/2 x squared, our g of x is 0. Let's see, I have 1/2 times 1/2 times 1/2. That's going to be rho over 8. We have x to the 4th from 0 to 2 dx. That's going to be rho over 8 of x to the 5th over 5 from 0 to 2. Now 2 to the 5th is 32. So you have rho times 32, and 2 to the 0 to the 5th is 0, over 8 times 5. Now the 8 and 32 are going to reduce, and you will have 4 rho over 5. For my, it's rho times the integral from 0 to 2 of x times 1/2 x squared minus 0 dx. So again, I'm going to pull this 1/2 out. That's rho over 2 times the integral from 0 to 2 of x cubed dx, which is rho over 2 times x to the 4th over 4 from 0 to 2. So that's going to be rho over 2 times 2 to the 4th is 16 over 4, and that'll give us 2 rho. So x bar is going to be my over m, which is going to be 2 rho over 4/3 rho. Like I said, the rows cancel, and we end up with 6 over 4, which is 3/2. Y bar is going to be mx over m, which is 4 rho over 5, divided by 4 rho over 3. That's going to be 4 rho over 5 times 3 over 4 rho, or 3/5. So x bar, y bar is 3/2, comma 3/5. Now 3/2, there's 1. Here's 3/2. 3/5, now this is 1. Right about here. So that would put the center probably right about there. And that's just an estimation, that's just a hand drawing. Okay. So we found the mass, we found mx, found my. X bar is my over m, y bar is mx over m. So let's go on to the next example. Feel free to pause that one. Okay, set up and evaluate the integrals for finding the area and moments about the x-axis and y-axis, x and y-axis for the region bounded by the graphs of the equations y equals 1 over x, y equals 0, and x is 1 to 4. So 1 over x is like this. We're going from 1 to 4. Okay. So our mass is going to be the rho times the integral from 1 to 4 of 1 over x dx. That's natural log of the absolute value of x, I forgot my rho, from 1 to 4. Oh, well, you have to find them. I need to find a. A is actually similar to this without the rho. Okay, I'll go back and do that. I guess we don't have to find, we just have to find mx and my, so we don't have to find the actual center of mass. Okay, so this is going to be rho times natural log of 4 minus natural log of 1. No rho, I forgot we're doing area. And that's just natural log of 4. Because natural log of 1 is 0. Mx is going to be rho times the integral from 1 to 4 of 1 over 2 times 1 over x minus 0, or plus 0, times 1 over x minus 0. So that's going to be rho over 2 integral from 1 to 4 of 1 over x squared dx. That's rho over 2 times what? That'd be negative 1 over x from 1 to 4. It's going to be rho over 2. Oh, it says rho is 1. I could have dropped rho off. Okay. And then we have negative 1 over 4 minus a negative 1 over 1. That's going to be rho over 2, negative 1/4 plus 1, or rho over 2 times 3/4, which is 3 rho over 8, and with rho being 1, it'll just be 3/8. And then my is going to be rho, integral from 1 to 2 of, this time it's going to be x times 1 over x minus 0 dx. That's going to be x times 1 over x dx. That's 1 to 4, not 1 to 2. So that's rho times integral from 1 to 4 of just dx, which will be rho times x from 1 to 4, which is rho times 4 minus 1, which is rho times 3. And with rho being 1, we just have 3. So our area is natural log of 4. mx is going to be 3/8, and my is going to be 3. Okay, feel free to pause. We'll go to the last page. Okay, use a graphing utility to graph the region bounded by the graphs of the equation. Use the integration capabilities of the graphing utility to approximate the centroid of the region. And I'll draw a little picture of this here. It's y equals x e to the negative x over 2. It looks something like this. We're going from 0 to 4. So our mass is going to be rho times the integral from 0 to 4 of x e to the negative x over 2 dx. By using the calculator, as instructions are, you get 2.3760 rho. mx is going to be rho integral from 0 to 4 of 1/2 times e to the negative x over 2. I forgot my x. X e to the negative x over 2 minus 0, or say plus 0, x e to the negative x over 2 minus 0 dx. That's going to be rho over 2, integral from 0 to 4, excuse me, of x squared e to the negative x dx. Because if you add these, negative x over 2 and negative x over 2 is 2, negative x over 2 or just negative x. So from that we get the calculator rho over 2. Let's give you one final answer here. 0.7619 rho. And my is going to be rho times the integral from 0 to 4 of x times x e to the negative x over 2 minus 0 dx. That'll be rho integral from 0 to 4 of x squared e to the negative x over 2 dx. And that'll come out to be 5.1732 rho. So we want to find our x bar is going to be my over m. That's 5.1732 rho over 2.3760 rho. And we get 2.177. And y bar is going to be mx over m. That's 0.7619 rho over 2.3760 rho. And from that we get 0.321. So our centroid is at 2.177, comma 0.321. We're going to go on to the last problem here. Feel free to pause that. Excuse me. The centroid is the center of mass. It's the balancing point. Okay. Okay, this is from the book number 35. Find and or verify the centroid of the common region used in engineering. Show that the centroid of the triangle with the vertices negative A0, A0, and BC is the point of intersection of the medians. Okay, let's draw a picture of this. So, excuse me, negative A, yeah, shouldn't do that far away. And some point out here, B comma C. Now when we talk about medians, medians would be the line that goes from the midpoint of one side to the opposite vertex. And then here, they always cross each other. And the intersection of all the medians is the balancing point. That would be the centroid. So we're going to show this mathematically one way, then the other way. The other way would be to actually find what these points would be, here, here, and then find these places of intersection. And really, we just have to find where two of them intersect to find that. Okay. When you look at this, by the way, here's C, and this is B. The height of this, let me change colors. The height of this triangle is C. So the area of the triangle is going to be 1/2 times, this is A, that's A, so 2A times C. And that's just going to be AC is the area of the triangle. MX is going to be integral from 0 to C, from 0 to C. I guess we need to come up with some equations first. What's the equation of this line here? What's the equation of this line? Okay. We'll have this, call this F2 of y, F1 of y. So what's our slope going to be? We're going to call this M1 for this slope. I'm really hesitant to use m's because it means mass as well, but m for slope. M1 is going to be C minus 0 over B minus negative A, or C over B plus A. Now we have the slope, and we have a point it goes through. So we can do, and we need to put this in terms of y instead of x. I'm going to solve for, do a find f of x, and then we'll convert back to get y. Okay. Y minus 0 equals our m, which is c over b plus a, times x minus negative a. So y equals c over b plus a times x plus a. Let's solve for x and multiply by the reciprocal here. So b plus a over c times y equals x plus a. And then we can subtract the a and have b plus a over c times y minus a equals x. Okay, so my f1 of y is b plus a over c times y minus a. That'll be for this side. Let's find it for the other side. What's the slope going to be? Okay, we're going to be doing C minus 0 over B minus A. B minus A. That's C over B minus A. And it goes through A0, so I'll do the same thing we did before. Y minus 0 equals C over B minus A times X minus A. So Y equals C over B minus A times X minus A. Multiply by the reciprocal. B minus A over C times Y equals X minus A, and we add A to both sides. So we have B minus A over C times Y plus A equals X. So F2 of Y, this side, will be defined by B minus A over C times Y plus A. Now, we're used to seeing this in terms of X, and so we go from right to left. Here we're going to go from bottom to top. So we have a curve here and a curve over here. A curve on the right, a curve on the left, instead of a curve on top and bottom. Okay, so we're going to go from 0 to C, and it's going to be that 1/2 times the one on the right minus the one on the left. Well, there's a plus and a minus. I think we'll do the plus first, then we'll do the minus. B minus A over C times Y plus A plus B plus A over C times Y minus A times B minus A over C times Y plus A minus B plus A over C times Y minus A. There we go. Okay. Let's work this out a little bit. Pull the 1/2 out front. And we're going to go with, looks like, lambda of just 1, so we don't have to worry about that too much. Okay, let's see what we have here. This is a B over C times Y minus A over C times Y plus A plus B over C times Y plus A over C times Y minus A times B over C times Y minus A over C times Y plus A, and this should be distributed as negative. And then we have a minus B over C times Y minus A over C times Y plus A, because of the double negative. Okay, let's see what's going to go away. A over C's go away, A over CY's, and the A's go away. Over here, B over CY's go away, and that's it. So we're left with B over CY plus B over CY is 2B over CY times negative A over CY minus A over CY, so it's going to be minus 2A over CY. A plus A is plus 2A. Okay. Keep going. We need to distribute. I can factor a 2 out of this group and a 2 out of here. That gives us 4 over 2 integral from 0 to C. If I distribute, I end up with a B over CY times negative A over CY, so it's going to be negative AB over C squared Y plus B over CY times 2A. That would be an AB over CY dy. So we'll end up with a 2 times what? Negative AB over 3C squared Y squared. It's 2C squared. Oh, wait, I have Y, that is Y squared. So this is 3C squared Y cubed plus AB over 2CY squared from 0 to C. And let's see how this cleans up. If I put C in there, what happens? Now we've got a problem with the 0 because we can't have 0 in the denominator, so we can't use that value. Let's put a C in there and see what happens. So we're going to end up with a 2 times negative AB over, okay, it'll be okay because it's a cubed, over 3C squared times C. Oh, wait, there's going to be a problem. Anyway, let me carry on. Times C cubed plus AB over 2C times C squared minus, oh, I'm sorry, the Y is going to be 0. I'm sorry, I'm starting to panic about nothing. Okay, minus the 0. So we end up with 2 times what? C's cancel, leaves a C. C's cancel, leaves a C. So we have negative ABC plus ABC. I feel like is there a typo there somewhere? Oh, my 3's. Over 3 over 2. There we go. And that's going to be 2 times the quantity ABC over 6, or just ABC over 3. Okay, that works. That's our MX. Okay, we found one of them. And we'll end up dividing by AC to get Y bar. Okay, that's our MX. So I'm going to pause for a second. If you want to pause this, and I'm going to need to erase this to get more board space. So if you want to be able to write this stuff down, write it down. Go ahead and pause now. Okay, let me count to 5. 1, 2, 3, 4, 5. Now I'm going to erase this and go on for the MY. Okay, on to MY. Shouldn't have erased that. Okay, now MY is going to be integral from 0 to C of Y times, we have our B minus A over C times Y plus A minus B plus A over C times Y minus A dy. So my is going to be integral from 0 to C of y times what? It's b over c y minus a over c y plus a minus b over c y minus a over c y plus a. So this is going to be, stuff's going to go away, b over cy, and we end up with integral from 0 to c of y times, okay, we have a over cy, negative a over cy minus a over cy, so minus 2a over cy. A plus a is plus 2a. So we have the integral from 0 to c of negative 2a y squared over c plus 2ay. And that shouldn't be too bad to integrate. So we're going to have negative 2ay cubed over 3c plus ay squared. Because it's y squared over 2 and that cancels. We're going from 0 to c. So we have negative 2a c cubed over 3c plus ac squared minus 0, putting 0 in for y is a 0. So we have negative 2a c squared over 3 plus ac squared, and that's going to be ac squared over 3. It's basically negative 2/3 plus 1 is 1/3. So our my is ac squared over 3. I need to erase the board again so we can get our center of mass. Okay, so I'm going to count to 5. 1, 2, 3, 4, 5. And we're going to pause. If you want to pause. Okay, so x bar is going to be my over our m, or in this case just the area, which is going to be, as we saw a second ago, ac squared over 3 over ac, and that's c over 3. So that's our y bar. Now the y bar is with my. X bar mx over a, and that's going to be abc over 3 over ac, and that's b over 3. So that the center of mass, or the centroid, is at b over 3 comma c over 3. So for y, it's 1/3 of the way up, and the x 1/3 of the way this way. I need to state, I had my labels wrong earlier because we're doing it in terms of y, not x, and so earlier the mx, what I had set for mx was, the first thing I did was really my, because we changed axes. And so that mx really is abc over 3, and that my is really ac squared over 3. But we did it with respect to y instead of x, so that's why I need to switch those labels, and I didn't do that. Okay, so that's what this engineering principle is that 1/3 of the way up and 1/3 of the way over here is going to be the center. So this is 1/3 B, and this is 1/3 C. That's where the center of mass would be. Okay, I think we're going to stop with that today. Yeah. So, I guess I'll see you on our weekly online chat time. So, talk to you later. Thank you.